Doppler effect. Consider a point source emitting waves in all directions. Here, let us consider it as a fire engine producing sound waves. Before continuing the topic, let's have a quick glance about two important terms, wavelength and frequency. The wavelength is the distance between two wave fronts. It is also the distance between crest of one wave to the crest of the adjacent wave, or the distance between trough of one wave to the trough of the adjacent wave. Frequency of a wave is the number of waves that passes a given point in 1 second. In this case, it is 2 waves per second, and in this case, it is 1.5 waves per second or 3 waves every 2 seconds. Now, let's get back into the concept. Here, the frequency and wavelength of the wave emitted by the source is same in all directions. Now, if the source emitting the waves is moving away from the observer, the wavefronts have to travel a greater distance to reach the observer. Therefore, the time taken by two successive wavefronts to reach the observer will become more. The wavefronts appear spread out. Due to this, the wavelength of the waves increases, the frequency and the pitch of the wave decreases. Similarly, if the source emitting waves moves towards the observer, the time taken by the two successive wavefronts to reach the observer will become less. The waves appear bunched up. Due to this, the wavelength of the waves decreases, the frequency and the pitch of the waves increases. This apparent change in the frequency of the wave caused by the relative motion between the source of the wave and the observer is called Doppler effect. Doppler effect has a wide range of applications. It can be observed in light as well. If a star emitting light moves towards Earth, then the frequency of the light received by Earth increases or the wavelength decreases. Thus, the spectral lines shift towards the blue end of the spectrum. This is called blue shift. Similarly, when the star moves away from the Earth, the frequency of the light decreases, the wavelength increases, and the spectral lines shift towards the red end of the spectrum. This is called red shift. If nu is the frequency of the wave at the source, v radial is the radial velocity of the source relative to the observer along the line joining the source to the observer, then the apparent frequency of the light wave nu dash is given by nu dash minus nu divided by nu is equal to minus v radial divided by c. Here, nu dash minus nu can be written as fractional change in the frequency, that is delta nu. Therefore, the equation becomes delta nu divided by nu is equal to minus v radial divided by c, which is equal to delta lambda divided by lambda. The value of v radial is taken as positive when the source is moving away from the observer, and the value of v radial is taken as negative when the source is moving towards the observer. Note that these formulae are applicable only when the velocity of source is far less than the velocity of light.